All right, so today we're going to talk about the ratio test. This is one of my favorite tests. It also actually works, all that has to happen is that you need to have a series with non-zero terms. As long as the terms are non-zero, it works. So it even works on alternating series. And specifically, you're going to use it for series where they're growing rapidly. So if you see exponential functions or factorials, or a combo of the two, or combo of polynomials and exponentials, anything that's growing rapidly, this is going to be a good time that you're going to use the ratio test. So the ratio test says that the series converges if the limit as n approaches infinity of a sub n plus 1 over an is less than 1. So what does this mean? This means if the next term divided by the previous term is less than 1, right? So the ratio of the next term divided by the previous term being less than 1 means that the next term is getting smaller than the previous term. Whereas here, if the next term is over the previous term is bigger than 1, then it's getting bigger, okay? Or if the limit equals infinity, then it diverges. So this is a pretty efficient test, helps us out a lot. And if it equals 1, that's the only time that it's inconclusive. So you would have to use something else. So let's see this thing in action. So we're going to take the limit as n approaches infinity of the absolute value. Remember, a(n) here is just 2 to the n over n factorial. So we'll have a(n plus 1 in the top. So that'll be plugging in n plus 1 in for n. And then divided by an. And you are taking the absolute value of this, and we want to see what this limit is equal to. So first we'll flip and multiply. And we can go ahead and drop the absolute value for this one, because as we go to infinity, everything inside of there is going to be positive. We've got exponential functions, which are going to just be positive, and the factorials will always be positive. So we can drop the absolute value at the same time. And we'll flip and multiply. So we'll have n plus 1 factorial and 2 to the n in the bottom. And then we're going to start simplifying. So a couple of things that we'll do to simplify. First, we're going to take the 2 to the n plus 1 and rewrite it as 2 to the n times 2 to the 1, because those are the same thing. And then I'll put the 2 to the n underneath this. And then remember, with factorials, a lot of the terms usually cancel out. So if we want to write out a few terms of n factorial, remember that would be n, and then the next one is subtract 1, and the next one is subtract another 1, dot, dot, dot. And then n plus 1 factorial, the first term will be n plus 1, and then you'll subtract 1, and you'll get n, then subtract 1, you'll get n minus 1, subtract 1, you'll get n minus 2, dot, 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 and those will start being the same. So we'll have a lot of things that cancel. The 2 to the n's will cancel. And then all of the n till forever will cancel with that. So all we'll have left in the bottom is 2 to the 1 in the top, or just 2, and n plus 1 in the bottom. And this limit as n approaches infinity, 2 is just a constant, will be 0 as the denominator grows. And that is less than 1, so by the ratio test, this converges. And just to re-emphasize here the cancellation that we did with the factorials, right? Remember, n divided by n plus 1, n factorial would be like saying 9 factorial. And then n plus 1 would be n, so 9 plus 1, so that would be like 10 factorial. And if you do 9 factorial, 9 times 8 times 7 times 6 times 5, dot, 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 and 10 will be 10 times 9 times 8 times 7 times 6 times 5, dot, dot, dot. And so the whole top one will cancel with everything except for the 10 in the bottom, which is exactly what we just did right here as well. Okay, let's do another example. So this one here, we'll do the limit as n approaches infinity of the absolute value. We'll do a sub n plus 1 in the top. So again, we're just plugging in n plus 1 wherever there's an n to find a n plus 1. And then a n in the bottom, because a n here is just n squared 2 to the n plus 1 over 3 to the n. And then we'll go ahead and flip and multiply. I'll go ahead and come down here. So we'll do the limit as n approaches infinity. Again, we can drop the absolute value here because as we go to infinity, n plus 1 squared will be positive, the exponential will be positive, 3 to the n will be positive, n squared will be positive as we're going to n. So everything there is already positive. So we can go ahead and drop the absolute value. It's not going to change anything. So we'll have n plus 1 squared in the top times 2 to the n plus 2. We'll go ahead and combine these terms right here. In the bottom, we'll have 3 to the n plus 1. And then we'll multiply by 3 to the n time. And then in the bottom, we'll have n squared times 2n plus 1. So this 2n plus 2, we can rewrite this as 2 to the n times 2 squared. And we can rewrite the 3n plus 1 as 3 to the n times 3 to the first power. And we can write this 2n plus 1 as 2 to the n times 2 to the first power. So we will have the 2 to the n's cancel. We'll have the 3 to the n's cancel. And then 2 squared is 4. So that will cancel with one of these 2's, and we'll be left with 1, 2. So then in the top, we'll have the limit as n approaches infinity. And the top will have n plus 1 squared left. And a 2. I'll go ahead and write that in the front. And then in the bottom, we will have just 3 times n squared left. Now, note you cannot cancel out this guy and this guy, right? That's very illegal math. You cannot do that, okay? But as we're taking the limit as n approaches infinity, now these are both growing at about the same rate here. So they're both n squared, so these are growing not at about the same rate, they're growing at the same rate. So we'll look at the ratio of the leading coefficients here to find our limit, which will be 2/3. And that is less than 1. So by the ratio test, this converges. All right, let's do 2 more examples here. So again, we see stuff growing really, really fast. This one's growing super fast because it's n to the nth power, super fast growing exponential function. And so we'll use the ratio test. Anytime you see factorials, usually the ratio test is a good idea. So we'll do the limit as n approaches infinity, absolute value, a n plus 1. So anywhere there's an n, we're going to put in n plus 1. So we'll have n plus 1 to n plus 1 power. And then we'll have n plus 1 factorial in the bottom. And I'll go ahead and flip and multiply. So we'll do so we'll do n factorial over n to the n. And then all of these things are going to be positive as we're going to infinity, so we can drop the absolute value. And we can rewrite this as n plus 1 to the n times n plus 1 to the first power. And then we'll rewrite the n factorial as n times n minus 1, dot, 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 just the first couple terms because we kind of see what's happening. And then the bottom we'll have n to the n. I'm just changing the order of these two so that the factorials line up. And then we'll have n plus 1 times n minus 1, and then these will start to be the same. So we will have a lot of the factorials cancel. This guy will cancel out with the rest of this. And then we'll have n plus 1 will actually cancel out as well with that extra n plus 1 that we had from this guy up here. And so then what we'll be left with is the limit as n approaches infinity of n plus 1 to the n over n to the n. And I'm actually going to write this as n plus 1 over n all to the nth power. So I'm just raising it all to the nth power. Okay, and the reason why I did that is because you might be thinking, oh, these are growing at the same rate because it's n to the nth power, but these aren't polynomials anymore, right? This is n to the nth power, not n to the third power. So we don't necessarily know exactly what's happening here, and this is actually a really special limit because this is the definition of the number e. Remember all those times that you've said, what the heck is this weird e value? It is the limit as n approaches infinity of this function. So this is the definition of e. If you look up what e is equal to, it's equal to this limit. And that is greater than 1 because e is approximately 2.7 something. And so this guy would diverge by the ratio test. Because the limit is greater than 1. Okay, let's look at one more ratio test problem here. So this is an alternating series. You don't have to apply the alternating series test here. You could try, but we're going to use the ratio test here because that's what we're practicing. So, and it works on alternating series, so that's pretty convenient. So we'll do the limit as n approaches infinity of the absolute value. We'll do a sub n plus 1, so replacing every n with n plus 1. And then I'm going to go ahead and flip and multiply a n. So we'll have n plus 1 in the top and square root of n in the bottom now. And then this one, actually, the absolute value does help us out because these guys, remember, are going to alternate between positive and negative, but the absolute value is just going to make them positive. So it's going to make those go away. And then as we're going to infinity, once we get above 1 here, everything else is going to be positive as well. So now the absolute values will go away and take those negative values with it, and we'll be left with the square root of n plus 1 times n plus 1 all over n plus 2. Actually, let's rewrite this. We'll move the square root over here and then n plus 2 over here, just so they're lined up nicely. Remember, this is multiplication. And so then we'll look at both of these. This part here, both are degree 1, so the limit there will be the ratio of the leading coefficients, which is just 1. And then here, these are also growing at the same rate, square root of n, and so the ratio of leading coefficients is what we'll be looking at there. So here, our limit is just equal to 1. So unfortunately, the ratio test is inconclusive here. This is pretty easy to use the alternating series test on, so you could try that if you wanted to. So we actually would want to use the alternating series test on this one, but I wanted to show you an example. Just because it is alternating doesn't mean you would have to use the alternating series test, but I wanted you to see one inconclusive version of the ratio test. All right, and then lastly, we're going to look at an example here of the root test, and this is not tested on the AP exam, but it's a pretty easy test to use, so I do want you to be able to use it, and if you continue in college level mathematics, you'll definitely see it, so it's good for us to be familiar with. So the way that the root test works is it works really well for things that are raised to the nth power. And so what it says is you do now the limit as n approaches infinity of the nth root of the absolute value of whatever a sub n is. And if that limit is less than 1, it converges. If it's greater than 1 or infinity, it diverges. And then 3, the ratio test is inconclusive. I'm sorry, root test. If the limit is equal to 1. So same conclusions as the ratio test, we're just now doing the limit as n approaches infinity of the nth root. So if you look at this series right here, both are raised to the nth power, so this would be a great opportunity to use the root test. But let's actually first rewrite this in a slightly different way as e squared to the n over n to the n, because this is the same thing where you multiply your exponents together. And then even further, then we'll go ahead and just rewrite it as e squared over n all to the nth power, since both the top and the bottom are raised to the nth power. So this would be a time to use the root test. So we'll do the limit as n approaches infinity. We'll do the nth root of the absolute value of e squared over n to the nth power. And when we do the nth root of something to the nth power, well, and all this is going to be positive as n goes to infinity, because we're going beyond 1, so all of that will be positive. So the absolute value will just disappear. It's not going to really change anything here. So we'll have the nth root of e squared over n to the n, and the nth root of the nth power just cancels out. So we'll be left with the limit as n approaches infinity of e squared over n, and then the limit as n approaches infinity of e squared over n is just going to be 0 because the denominator is going to grow and the numerator will stay the same, which is less than 1. So we would say this series converges by the root test.